This is lecture 13. So today we will start a new topic, that is stability of linear time invariant systems. So this is the fundamental requirements in control system, because if you have a control system, the first requirement is the system should be stable, otherwise you cannot do anything on that system. So if the system is unstable, you need to design a controller to stabilize it. So it is very important to all of us to know what is the stability of linear time invariant system. As I have already pointed out that in this course we will be only discussing linear time invariant system. So today the lecture will be considering only this class of system, and we'll see the various definitions of stability, because that depends on what type of system and the point of view you have considered. So there are many definitions of stability. So there are many definitions of stability, and it depending upon the type of system, that means it is LTI or linear time invariant or time varying or linear or non-linear. So what type of systems you have considered, what type of systems, and the point of view considered. So now I will be discussing in detail, that means what is the meaning of that point of view. So in case of linear time invariant system, the total response is actually that natural response and the forced response. So that is the total response. I think already you have studied it in signals and network, LTI system. Equal to that natural response. What do you mean by the natural response? That means when there is no input applied to that system, the system will be driven by its initial condition. So because of that initial condition, the system would show some response. So that is called that natural response. So it is also called zero input response, because externally you are not applying any input to that system. So that's why it is called zero input response. So basically this is due to initial condition, and the other one is that forced response. Forced response means the response of that system due to the forcing function. So due to forcing function. So that means whenever you have one LTI system, so the response of that system depends on two factors. One is that initial condition, and other one is the forcing function that you have applied. So from this particular fact, it is now clear that we can see the stability of a system from two point of views. One is that natural response point of view, another one is that forced response point of view. So let us first discuss what is that natural response point of view. That means that response only for the initial condition. So in that case, we assume that the external force applied to that system equal to 0. So from natural response point of view, so here you can see whenever you have started discussing that stability, I have pointed out that means what point of view we have considered. Depending on that, we can give the different notion of stability. So here first we are considering that natural response point of view, and next we will be considering that forced response point of view. So natural response means external force applied to that system equal to 0. So you would say that the system is stable in natural response framework if the response approaches 0 as t tends to infinity. So it is called stable. It is called stable if the response approaches 0 as t tends to infinity. So this particular stability is called asymptotic stability. So that means whenever you have a system, suppose that system has some initial condition. So suppose this is that time response of that system, so that xt. Now the response that we would have, it is only because of that initial condition. So suppose that response is like this. So then you can see here, that means when time is tending to infinity, this response goes to 0. So this particular stability is called that asymptotic stability. So this is the point of view what we have considered, that is that natural response point of view. That means externally no force is applied to that system. Now the second thing is what is unstable. The system is called unstable if the response tends to infinity as t tends to infinity. So in case of linear time invariant system, this is the property. That means within finite time, if the system is stable, the response cannot go to infinity. So it would take infinite time to reach at infinity. So here we can see one unstable behavior like this. So this is that time axis, and this is suppose one state or output. So here suppose your response is going like this. So that means here you can see that when time is tending to infinity, the response is going to infinity. So this is a typical response, unstable response. So and we have assumed that okay, it has some initial condition, and suppose that initial condition it is a 0.1. So this is, suppose you have taken that 0.1 and 0. So this origin is a 0.1 and 0, and when time tends to infinity, then it goes to infinity. So this is actually one typical response of unstable system in natural response framework. Now the third one is marginally stable. Third one is that marginally stable. if response neither decays nor grows but remains constant or oscillates. What is that? So here actually we have seen three terms. One is, you can see that stable, another one is that unstable, and the third one is called that marginally stable. So that means there are three different notions we have seen in the natural response point of view. So here you can see what is called marginally stable. In this case, you can see that the response decays to 0, and say suppose this is 0 0, so the response decays to 0, and in this case you can see that response grows to infinity. So what is marginally stable? Marginally stable is that response neither decays, that means the case 1, nor grows, that case 2, but it remains constant or oscillates. So that means if we draw a typical response, so typical response if we draw, so suppose this is the time t and you have that xt here, suppose you have some initial condition, and then it might happen that it remains constant, or it might happen that it oscillates. So this is the typical response of marginally stable system. So we have seen three different notions of stability of linear time invariant system in natural response framework, that is stable, unstable, and marginally stable. And we have seen the typical behavior time response of that system. So this is that stable behavior, and this is that unstable behavior, and this is called that marginally stable behavior. So now we'll be discussing the other point of view, which is called that forced response point of view. That means in that case, we consider that some input is applied to that system. Forced response point of view. So in this case, there are two notions. One is that stability, another one is that unstability. So the system is said to be stable. That means whenever some external input is applied to that system, the system is said to be stable if every bounded. So this is very important, that every bounded signal, every bounded inputs, else a bounded output. That means whenever we apply a bounded input to that system, the system would show the bounded response. So here we can see one typical behavior, like suppose this is t and say suppose this is yt. If we apply some bounded input like say step input, so this is that input, and we can see that okay, the output is coming like this. So that means this is that input, and this one is output. So you can see that the output response is bounded whenever you apply a bounded input. And this is for all bounded input signals. This is important, every bounded signal. So if you find one bounded signal for which we are getting some unbounded output, so then that is not a stable system from force response point of view. So it has a name called that BIBO stability. BIBO stability. So this particular notion is called BIBO stability. So BIBO stands for bounded input, bounded output. So BIBO, this is very important in case of linear time invariant systems, that is called bounded input, bounded output. So bounded input, bounded output is abbreviated as BIBO. So that means for every bounded input signals, if we have bounded output, then it is called that BIBO stable. And this particular notion, definition, we are discussing from force response point of view. Now, when it is called unstable, it is unstable if any bounded input. So if you can find any bounded input, else and unbounded output, then it is called unstable system. So it is for any. So that means if you have a system, if you can find a bounded input for which you are getting unbounded output, so then that system is called unstable system. So let me summarize what we have seen. That means we can give many definitions of stability of LTI systems if we consider the different point of views. So natural response means when that external input applied to that system equal to 0, and there we have seen there are three notions of stability. So one is that stable, and the second one is that unstable, and the third one is that marginally stable. So in case of marginally stable, it neither decays to 0 or grows, but it remains constant or oscillates. So three different notions we have seen in natural response point of view, and from force response point of view we get the two definitions. One is that stable, which is called that BIBO stable, bounded input, bounded output stability. Another one is that unstable. So here I think some remarks are important. So let us discuss one by one. That means some important facts involved in the stability analysis of linear time invariant system. So let us first discuss that we consider some example. So suppose you have, let say GS is a transfer function which has that transfer function that is a square plus 1. So this is that output by input. So now if you apply that input, suppose the input that you have applied, that is ut equal to, say, let us put some signal that is say rt equal to sine t into ut. So here that ut is that unit step function. So that means when t less than 0, this rt signal equal to 0. So now if you take that Laplace transform of that us, so then you have that 1 by s square plus 1. So now if you apply this particular input, that means you have that GS function and you have applied that input RT, then what would be YT? So it is very simple. If you take that Laplace transform and inverse Laplace transform, so you would get that YS equal to 1 by s square plus 1 whole square. So then that YT that you would have, that is T into sine T. And you can see that this is that response that you would have whenever you apply this input to that system, GS equal to that. And it is clear that at T is there, so when time is tending to infinity, then that YT also will be tending to infinity. So obviously it is one unbounded response, and as you have applied input externally, then we'll be considering this particular notion, that means from force response point of view, and you can see that this particular definition is applicable to this particular case, because we find any means, suppose if you have this system and this is one input, if we apply that one, we can see that it is tending to infinity when T tends to infinity. So this is one unstable system. So that means from this particular point of view, if you consider the force response point of view, we can see that the system is unstable. But if you look at that particular system, that is a square plus 1, so it has two poles on the imaginary axis, that is plus minus j, and from this particular point of view, that is natural response point of view, whenever there is no external force, you will see that the response would be oscillatory. So that means in this particular example, we can see that the system would be marginally stable, whenever we consider the natural response point of view. That means in this case, external input equal to 0. But if we consider the force response point of view, that means whenever you apply some input, then you will see that there is one input, at least we get it here, this input, so that the system response is unstable. So that means from force response point of view, we would say that the system is unstable. But from initial condition point of view, that is natural response point of view, we would say that this is marginally stable. So this is very important. That means here let us write, although sine t is a bounded signal, and here you can see that this signal is a bounded signal. So here you can see the definition, any bounded input. So this sine t is a bounded input, but we are getting some unbounded response. So let us write, that is, although sine t is a bounded signal, yt that we have obtained here, yt is unbounded as t tending to infinity. That means when t is very large. Hence, GS, that is that system, is not BIBO stable, bounded input, bounded output stable. That is, it is unstable. The marginal stability that is from natural response point of view, the marginal stability in view of natural response is unstable from BIBO perspective. So this is very important. What is that? That means suppose a system is given to you. So then if you consider the natural response point of view, that means no input is applied to that system. If that system is marginally stable, but the same system would be treated as unstable whenever you consider this force response point of view. So this is one example. So that means from bounded input, bounded output concept, the marginal stability in view of natural response is treated as unstable system from BIBO perspective. So that means if someone asks you that whether the system is bounded input, bounded output stable or not, if it is marginally stable, then your answer would be no, it is BIBO unstable. So this is very important concept. The second one, what we are going to, so suppose we say that this is that first remark, then the second remark is whenever an LTI system is given to you, what is the condition for BIBO stability? So suppose we consider the zero initial condition. So suppose we write that with zero initial condition, so now we are just trying to find the condition for bounded input, bounded output stability. With zero initial condition, the system is BIBO stable if its output YT is bounded. That we have discussed. I am writing it again to better understand it. To bounded input UT. So now whenever you have a system, in the transfer function we have already studied what is transfer function. That is actually the Laplace transform of the impulse response. So now here we can write that what is the relationship between this input and output, because the convolution is involved. And here we can write that YT, that output is that integration 0 to infinity, and ut minus tau, or in other way you can write that gt minus tau ut e tau d tau. So this relationship already we have seen, and here this g tau is the impulse response. We have discussed in detail, is the impulse response. And as the system and signals are causal system, so here you can put that 0 to infinity, because 0 to t and 0 to infinity, both of them would be same in this case. So now this is that output of that system, LTI system. So now if you take the magnitude of that output, so for better understanding we are taking that considering single input single output case. So if you take mod of that YT, so then you take that mod of this particular integral t minus tau g tau d tau. Now you apply the triangular inequality, that is u t minus tau g tau d tau. So we have applied, if we apply the bounded input, so applied that bounded input, that means here let mod of ut is less than equal to m. That means it is bounded signal, because it is bounded input. So then if we just replace it here, because ut minus tau, so if we replace it here, what will we get? So we'll get that it is less than equal to 0 to, say here m is that constant, so 0 to infinity g tau d tau. Here, from here we can write, just in place of this one we have replaced this m. So now you can see here, if the system's output yt is bounded, so this yt is bounded, then what happens? So if the system's output yt is bounded, so that means this one is bounded means what? We have, suppose say yt is less than equal to n, and as it is bounded, that should be less than infinity. So then from here what we can see, that yt mod of this one is less than this particular term. So if this particular term is less than n, so then what we have, it is a sufficient condition. You can see here, if n integration 0 to infinity, that g tau d tau is less than equal to n, less than infinity, that is there exists a finite positive q such that, so here you can see that if this particular term is less than n here, so then we have 0 to infinity, that g tau d tau is less than q. That means if we divide this n, so divide this n by this m, that means n by m, that is equal to q. So then what we have, we get this particular relationship. You can see here, that is that integration 0 to infinity, the mode of the impulse response of that system, it should be finite. So then if this particular condition holds, then the system is BIBO stable, bounded input, bounded output stable. So one important result we have seen here, you can see that what is the condition for BIBO stability. Whenever you have a system, in case of LTI system, we always have this particular relationship, and then we have taken the modulus mod of that yt, and we have applied that triangular inequality, and we found that the input would be bounded and output would be bounded if and only if we have this particular condition. That means 0 to infinity, the mode of g tau. So this g tau is that impulse response of that system, LTI system. That is that impulse response of that LTI system. So this is that condition. So suppose one LTI system transfer function is given to you, and if you are asked whether the system is stable or not, so this is a condition. If you check that one and if it holds, then you can say that the system would be BIBO stable. So now let us see the other important things. That means the asymptotic stability already we have discussed here. The asymptotic stability, that means whenever you can see it here, the asymptotic stability. And interestingly, the asymptotic stability or the BIBO stability, so all these concepts or notions in case of linear time invariant systems, they are actually the equivalent. So let us see. say asymptotic stability. Asymptotic stability means that yt reaches 0 as t tends to infinity when ut equal to 0. That means no external input is applied to that system. So asymptotic stability. So yt reaches 0 as t tends to infinity when ut external input applied to that system equal to 0. So in case of LTI system, this is very important that because this asymptotic concept is actually in natural response framework. You can see here the asymptotic stability is the notion that we have obtained from natural response point of view, and BIBO stability that we have obtained from force response point of view. So here, whenever we are talking about that asymptotic stability, we make that ut equal to 0. But interestingly, in case of LTI system, the asymptotic stability implies BIBO stability. So this is very important result. That means whenever a system, LTI system is BIBO stable, then that is also asymptotically stable. Or if you have a system which is asymptotically stable, that also would be BIBO stable. So now let us see how the stability, the asymptotic stability or BIBO stability in case of LTI system is related to the poles of a transfer function. That is very important, because just by looking at the pole location of the transfer function, we'll be able to say whether the system is asymptotically stable or BIBO stable or not. So here we'll see that if any pole of a transfer function lies in the closed right half of that S-plane. So here we'll be just considering that this is that S-plane. So this is S-plane. That means that is sigma and this is j omega. And we'll consider the two parts. One is that this part, that means this is that called open, this is called that closed, this is that closed right half plane, and this is called open left half plane. So why open? The reason is in this case that imaginary axis is excluded, and closed, the reason is the imaginary axis is included. So that's why it is named as closed right half plane and open left half plane. So the system is asymptotically stable or BIBO stable if all the poles of that systems lie in the open left half of that plane. So we'll see it by some simple mathematical derivation. Let us see. So for LTI system, and mind that this is only for linear time invariant system. For LTI system, BIBO, bounded input, bounded output, and zero input stability and asymptotic stability all have the requirement that the roots of the characteristic equation so characteristic equation means whenever you have a transfer function that is gs equal to numerator polynomial divided by denominator polynomial. So the denominator polynomial is equal to 0. That gives you the characteristic polynomial. Or if you are in state space framework, the determinant of lambda I minus a equal to 0. That gives you the characteristic polynomial. We have discussed those things in that modeling part. That characteristic equation all be located in the open left half of S-plane. So this is a very important and powerful result in linear time invariant system theory. So here you can see that all the poles should be in the open left half plane. So this is not the closed one. That means if you have any pole in the closed right half plane, any pole, so suppose it is on the imaginary axis here, or suppose it is here, so any pole on the right hand side, so that is actually that unstable. This is that unstable zone and this is that stable zone. So that means if any pole in the right half of the closed right half plane, so then it is called unstable system. And when the pole lies, all the poles lie in the left half of that open left half plane, then it is called stable system. So let us see a simple thing, that means how to show that this particular thing works. So here you can see that gs is the transfer function, and we know that this is actually that Laplace transform of the impulse response gt. So then if you just write it using the definition of Laplace transform, that is gt e to the power minus st dt. So then that is 0 to infinity, that gt as s equal to sigma plus j omega. So we can write that e to the power minus sigma t into e to the power minus j omega t dt. So now if we take the mod of gs, so here you can see that if we take the mod of that gs, then the mod of this one equal to 1, and so this is, we can write that 0 to infinity the mod of gt, the mod of e to the power minus sigma t dt, as the mod of this one equal to 1. So that's why you can write it like this, because if we take the mod of this and then apply triangular inequality, so then that would be less than equal to. So now let S be a pole of that system. So let S be a pole of GS. So as you know that when S is a pole of GS, so then GS would be infinity, because at pole location the transfer function is infinite. So then GS equal to infinite. So then from this particular relationship we would have that infinity, because this GS would be infinity, is less than equal to 0 to infinity gt e to the power sigma t dt. So whenever S is a pole of the transfer function, so at that particular point this particular relationship holds. So now let us consider that pole. So suppose any pole lies on the right half of that S plane. So whenever it lies on the right half of that S plane, closed right half of that S plane, then what would be the sigma? This sigma would be that real part. That means you can see here the sigma is here. That means this sigma either would be equal to 0 or it is greater than 0. So it is sigma is greater or equal to 0. So that means if you have a pole which is lying on the right half of that S plane, so then the sigma, corresponding sigma, would be greater or equal to 0. So let us see then what happens in this case. So if any pole is on the closed right half, closed means, as we have pointed out, that means it includes the imaginary axis, closed right half of S plane. So then if you just look at that sigma, so this sigma, it is positive or 0. So then this value would be always less than equal to 1, since sigma is greater or equal to 0. So that means here you can see if this is less than equal to 1, so we can write that then it implies this particular right half, this relationship. So this implies that left hand side is infinity is less than 0 to infinity g tau d. So this one is dt. So then what we have seen, that means if any pole lies in the closed right half of that S plane, then we get this relationship. That means 0 to infinity, the impulse response, its absolute value, if you take, so then it is coming greater or equal to infinity. But what we have seen here, what is the condition for the BIBO stability? That means 0 to infinity, absolute value of that g tau, it should be less than infinity. That means it should be finite. But what we have seen, if any pole lies on the closed right half of that S plane, this particular expression is coming infinite. It is greater or equal to infinity. So that means it is infinite. So that means the system is unstable. The system is unstable. So from this particular remark, what we have seen, that means if you consider one LTI system, linear time invariant system, if any one pole lies in the closed right half of that S plane, that means it may lie on the imaginary axis or on the right half of that S plane, the system becomes unstable. So for testing stability, you need to ensure that in case of LTI system, all poles should be in the open left half of that S plane. If any one of them goes to closed right half of S plane, then it would be unstable. And another thing is the poles. So this remark is that 4. Okay, so now this is 5. poles of multiplicity greater than 1 on the imaginary axis lead to the unstable response. Poles of multiplicity greater than 1 on the imaginary axis lead to unstable response. That means the system would be unstable. So here what is that? So you can see that suppose you have a transfer function Gs that is 1 by S. So this is a pole. In this particular case there is a pole at the origin. So this gives you that marginal stable response from zero input point of view, zero input response point of view. But if you have say Gs equal to 1 by S square, so it gives you that unstable response. So that means whenever you have pole on the imaginary axis with multiplicity greater than 1, so here the multiplicity that is 1, so here you can see that multiplicity greater than 1, here 2. So in this particular example the multiplicity is 2. So multiplicity equal to 2 in this case, and you can see here that the system response would be equal to T. Suppose if you apply a bounded input, say suppose if you apply one input unit impulse, so in that case you can see that Gs would be 1 by S square and the output Yt would be equal to T, that is ramp type of signal. So when T tends to infinity, it goes to infinity. So then it gives you that unstable response that we have studied. And in this case, you can see it remains constant. So that's why whenever a system has poles on the imaginary axis with multiplicity greater than 1, then it gives you that unstable behavior. So from here, what we have from this particular discussion, what we have seen, so that is unstable systems have closed loop transfer function functions with at least one pole in the right half plane. RHP stands for right half plane, and or poles of multiplicity greater than 1 on the imaginary axis. So that means whenever you have a system with transfer function, say transfer function is given, so in that case the system would be unstable if it has at least one pole on in the right half of that S plane, or if it has a pole on the imaginary axis with multiplicity greater than 1. So if you find that type of transfer function, then immediately you can conclude that the system would be unstable system. So let us take one example here. So suppose you have a plant transfer function that is a 10 s plus 2, and here you have that s plus 4, s plus 6, s plus 8, and s plus 10. So this is one open loop system, and here you can see that the system has poles at origin, then at -4, -6, -8, and -10. So they have, they are all in the left half of the test plane and one pole at origin. So from zero input response point of view, you can say that this is stable and this is marginally stable because one pole is at origin. But what happens if you just close that loop? Because this is that open loop system. If you close that loop, say this is that so this is RS, this is that negative feedback, and if you close that loop, then what is that closed loop response? So the closed loop response, that is Ys by Rs, so that is that Gs by 1 plus Gs. So if you simplify that one, you would have S plus 2, then if you just multiply, then you have that s to the power 5, 20s, s to the power 4, then 284 s to s cube plus 1232 s square, 1930 s and 20. So this is that closed loop transfer function, that is Ys by Rs. So now the question is, what are the locations of closed loop poles? Because the open loop case we have seen that these are the poles. So now if this is that question, what are the location? What are the location of closed loop poles? Because what we are trying to do here, so we have given one open loop system, and just by looking at the location of that pole, we can see that it is marginally stable. But whenever we close that loop, we need to understand whether this closed loop system is BIBO stable or not. So for BIBO stability, now we are trying to understand the stability just by looking at the location of that poles. So here we can see that this is the transfer function and this is that characteristic equation. So roots of this characteristic equations are the poles of that system. So now the necessary condition for the all poles will be in the open left half of S plane if all the coefficients, so here you can see that the coefficients are here 1, here the 1, 28, 284, 1232, 1930 and this one. So all the coefficients should be present and they should be with same sign. That means here you can see this is positive, this is positive, this is positive, this is positive, this is positive. So these are the two necessary conditions for being all the poles should be on the open left half of the S plane. So that means whenever we find that any one of them is violated, then immediately we can conclude that the system would not be stable. So let us write those necessary conditions. So the necessary conditions for stability. For stability means all poles should be in the open left half of that S-plane. So that is that asymptotic. So asymptotic stability or BIBO stability. So that means all coefficients are with same sign. So here all coefficient means all coefficients of the characteristic equation. So this is the characteristic equation, and here you can see that the coefficients are here s to the power 5, then s to the power 4, then s to the power 3, then s to the power square, then 1, then 0, s to the power 0. So this is that polynomial, characteristic polynomial, and here we can see that all coefficients. So all coefficients, so that means here 1, 28, 284, 1232, 1930, 20. So all coefficients are with same sign. So this is one of the necessary condition to be stable. System is to be stable. And the second necessary condition is all coefficients should be present. So that means here you can see that 5, 4, 3, 2, 1, 0. So all the coefficients are present. So these are actually the two necessary conditions. So if I just take one simple example, so suppose your characteristic equation. So one example here, you can characteristic equation. If you have a characteristic equation like, so suppose s to the power 3 minus 2s square plus 5s plus 6 equal to 0. So now you can see here that the coefficients here 1, then minus 2, 5 and 6. You can see here the first condition is violated. That means all the coefficients are not with same sign. So here minus 2 is there. So that means if you find the roots of this characteristic polynomial, you will see that at least one of the root would be on the right half of that complex plane. So that means S plane. So that is, the system would be unstable. So no need to find what would be the location of that roots, because the necessary condition is violated. So in other case, if you have one particular say characteristic polynomial, suppose this is S cube, say suppose this is s to the power 4 plus 5s cube, then say 2s plus 6 equal to 0. So in this case you can see that s square is absent. So as one particular coefficient is absent, that means here you can see s to the power 4, 3, then 2 is square term is absent. So that's why the second condition you can see all coefficients should be present, but here you can see that the coefficient associated with a square, we can say that that is 0. So it is actually absent. So then if you find the roots of this particular characteristic equation, then you will see that at least one of the roots will be on the right half of that S plane. So that means that is also unstable. So from here what we have understood, that means whenever a system is given, so first you need to consider that characteristic polynomial, and if any one of the coefficient or any one of the necessary condition is violated, so then that system would be unstable. So that means if any of the above condition, any of the above conditions fails, that means the necessary conditions fails, the system is not stable. So in that case, we can say that this is actually the sufficient condition for instability. Sufficient condition for instability. That means if you find any one of the condition holds, that means either the coefficients have different sign, or any one of the coefficients at least missing from the characteristic polynomial, then you can say that the system would be unstable. So today what we have discussed, so we have started with the different notions of stability, and we found the two perspectives. One is that natural response perspective, another one is that force response perspective, and we found that asymptotic stability, BIBO stability, both of them are the same notion in case of LTI system. And we found the condition for BIBO stability, that means whenever that GT, that is the impulse response of the LTI system, is given, and if you take the absolute value of that one from 0 to infinity, if you take integration, it should be finite. And in transfer function domain, we found that if an LTI system is given, and the system would be stable if all of its poles lie in the open left half of that S-plane. And then we found that if the system has poles on the imaginary axis, then it would be marginally stable, but if the multiplicity is greater than 1, then it would be unstable. And here we have taken one simple example, and we have discussed two necessary conditions for stability. That means all coefficients should be with same sign and all coefficients should be present. So whenever we have one characteristic equation, and if we find that any one of the necessary condition is failed, so in that case directly we can conclude that system would be unstable. Thank you.